Hello and welcome to today's webinar organized jointly by Friendship Systems and R&D CFD. Wherever you're sitting, good morning, good afternoon, good evening. A few housekeeping informations before we actually get started. So first of all, you have the option to ask questions in the interface of GoToMeeting. You can post your questions. If we have enough time at the end of today's webinar, we will try to answer these questions live. Otherwise, we will get back to you by email, so don't hesitate to ask anything that you want. And also at the end of this webinar, there's going to be a small questionnaire with just 5 questions. It might take less than a minute to answer, so of course, I'd be happy if you fill out this questionnaire. So let's get started. Today, I'm joined here by Giuseppe Cicalese. Giuseppe is CEO and co-founder of a company called R&D CFD, and he will tell us a little bit more about this company later on. Giuseppe has a PhD in CFD simulation of multi-phase and multi-component flows in internal combustion engines, so definitely the right guy to talk about powertrain components and optimization of powertrain components. Myself, I'm currently head of sales for Europe at Friendship Systems. I previously worked for a long time here in the company in pre-sales and engineering, and I've been with the company for about 10 years. I'm originally a naval architect, so not much to do with the topic we talk about, but I've worked on many projects in this field, so I hope I can bring enough expertise into this matter. The agenda for today, so we will start first of all by, I will introduce the company Friendship Systems very briefly and our software CAESES and its capabilities. And then, as I mentioned, Giuseppe will tell us a little bit more about R&D CFD and the consulting services that they offer. And then we want to look at a specific application case, which will be an intake port optimization. So we will present that case. We will talk in more detail about the geometry model that we have set up for the variation of this geometry. And then again, Giuseppe will tell us about the simulation setup and the optimization setup and the results that we obtained for this case. And finally, of course, there's going to be a small wrap up. So to start with Friendship Systems, who are we? We are a company, a software company mainly, that partners up with our customers to solve any kind of problems that they encounter in the so-called simulation-driven design process. The company exists since 15 years, and we have a lot of experience in the fields of geometry parametrization, specifically of complex geometries, as well as optimization. Just as myself, the company also started in the maritime industry, and we're located in Potsdam in Germany. What you see here is unfortunately not our office, but one of the beautiful palaces that you can see around Potsdam if you ever come here. So we mainly have one software product, which is the CAE platform CAESES. And now I want to tell you more about CAESES. So what do we do in this software? The software has a few different components. The first of all is the optimization part. So here it offers all the algorithms that you would need to drive an optimization process or simply a DOE process. And when you generate all the data during the optimization, you have to manage that data somehow. It's geometry data, simulation data, other kinds of results, and that needs to be organized and managed. And finally, you need assessment tools to analyze this data and draw your final conclusions from the optimization process. The second and probably most important component of CAESES is the CAD part. We have a specialized CAD inside of CAESES that is focused on providing geometry models that are ready for simulation, so that don't need any kind of, let's say, manual interaction before you send them over to your simulation tool. Another very important focus that we have is on geometry variation. So in many traditional CAD tools, you can build geometries in all kinds of shapes, but they have a bit more problems when it comes to variation. So that's what we're focused on. And another important point is the efficient parameterization of the geometry, so that you describe your geometry with as few parameters as possible, which definitely helps you to save time in the optimization process. And to complete the whole process, we have a generic interface that can be used to couple our software cases to any type of external simulation software, most often CFD tools, that will then, in the optimization process, take care of the meshing and the solving and possibly post-processing of these cases. So the first question, which I think maybe is not so difficult to answer, is why should I automate my design process with cases or in general? And the situation that we have is that laws and regulations, but also the tough competition in the market, demand a very high level of performance in modern engine design. So the, let's say, old type of process where you have a manual iteration between your CAD generation, creating a mesh, running CFD, and then post-processing the results, and then going back to the beginning. This type of process is time-consuming for one, which of course increases development costs. And it can certainly lead to an improved design by iterating in this way, but not necessarily to an optimized design, so that there's going to be failure to meet the design targets. The automation, on the other hand, can shorten the development times because you can run everything in an automated process without user interaction. Can reduce the design cycles. And I think apart from leading, of course, to better and optimized design, I think an important point is that you can also increase very early the knowledge about the behavior of the product with respect to changing parameters and the feedback in terms of performance that these changes have. And of course, our tool CAESES is intended to give you control over this design process from an integrated and single user interface. Another question, which for many people I know is a bit more difficult to answer. I told you CAESES is or a very important part of CAESES is this CAD system. So the question might be, why do I need another CAD system? So maybe you have already a traditional CAD system that is used to run the whole PLM process, CATIA, NX, Creo, whatever. And why do you need to include another additional CAD system into your process? The situation here is that most of the typical bottlenecks that we encounter and our customers encounter when they want to run an optimization or design exploration process are actually related to the handling of the geometry. So in traditional CAD systems, for example, the geometry variation is often difficult or prone to failure. So it means you're changing some parameters and then the model fails to regenerate. Another point is that it is often difficult to consider, or maybe that's one step further, automatically fulfill certain constraints for manufacturing and so on. And another bottleneck that is related more to the structure, how the companies work, is that the simulation engineers often depend on the CAD department to provide geometry variants. So if they want to change something in the geometry, they have to ask the CAD department to provide the new geometry. And that, of course, as you can imagine, not only costs a lot of time, but also is not really suited for automation. The final point is that the quality of the CAD model that you get from the CAD department might not necessarily be suited for simulation in terms of water tightness, for example, or the level of detail that this model comprises. And these are basically the facts that we're trying to address with our specialized CAD system in CAESES. So let's have a look at some powertrain applications that you can use this system for. The first of these is ports, which we will talk some more about today. Here you would like to directly control flow relevant parameters in the port geometry, for example, the distribution of the cross-sectional area along the path of the port. Maybe some specific aspects like considering blocking due to the valve bossing and stem that you want to consider in your cross-sectional area distribution, things like that. But we will see more about ports later on. Another application in the field of powertrain are manifolds, exhaust manifolds, intake manifolds. Here often an important point is the consideration of packaging constraints, and we have the possibility in CAESES to do a distance check to neighboring components so that you can make sure when you're varying the geometry that a certain minimum distance between the components is maintained. And we have done some work on this in the past. A very interesting aspect here is to also couple 1D and 3D CFD solutions where you consider the whole engine system with a 1D systems simulation, and the manifold is then computed in detail using a 3D CFD solver. Another application are turbo and superchargers. So here we have a lot of capabilities to do a detailed parametric modeling of the impeller geometry, but also the volutes. You can combine flow aspects with structural aspects for the turbine blades, for example, the strength and vibration connected, of course, to their flow behavior. Another application that we have also talked about in the past in the last webinar that we ran in the field of powertrain is in-cylinder geometries, like a piston bowl that is shown here for a diesel engine. Here, an aspect in terms of constraints is the compression volume that should be kept fixed for all variants that are created, and this can be done in an automated way in CAESES so that you can change the geometry of your bowl and keep the compression volume fixed automatically so that all variants that are generated are feasible. Of course, you can combine the geometry optimization with other parameters related to the simulation, like injection timings, injection profile, spray angle, things like that can be taken into account in the optimization in parallel with the geometry optimization. Exhaust systems are also another application. So here we have all kinds of ducts, diffusers, or urea mixers, things like that. Here we can use, of course, parametric morphing-based approaches, or an example that we also see here is the optimized routing of exhaust tubings under consideration of packaging. And many more applications in the field of powertrain that I'm not mentioning specifically now. So finally, how can you make use of CAESES? There is basically two ways that can be used. The first of all is as a so-called user. So a user uses pre-configured models and setup. This doesn't need any training, so you don't need to learn how to use CAESES in detail. And you can make use of generic models that are provided by us, by Friendship Systems, or custom-made models that we can also provide. Or if you have an internal developer, so an internal CAESES expert that can create these models, then other people in the company can make use of that. The interface is either the actual graphical user interface of CAESES, or we also have the possibility of wrapping projects into a web interface that can be used in a very easy way and allows just limited access to a certain setup, parametric model, optimization setup, and so on. And the second option is as a so-called developer. So this is basically the CAESES expert that is able to create complex parametric models or optimization setups for his own use or for other users in the company. And this, of course, needs a certain amount of training. And as I mentioned, it can support internal users, but also offer his services as a consultant. And that's so much for a short introduction about CAESES and friendship systems. And now I will switch over to Giuseppe, who will tell us more about R&D CFD.
Good afternoon, everybody. Thank you, Mattia, for your introduction. I am Giuseppe Cicalese, and I am the CEO of R&D CFD. We are a spin-off company of the University of Modena and Reggio Emilia. And we are located in Modena, that is in the middle of the Motor Valley, the so-called Motor Valley. We were born a little bit more than 5 years ago, and we are at the present moment 7 CFD engineers plus 5 high-level CFD specialists, and we offer to our customers high-level consultancy on fluid dynamic topics. Of course, we are mostly focused on engine-related and powertrain-related topics. We have our own computational resources that is, of course, fundamental in order to give a high-quality service. And we are, since a couple of years, sorry, a partner of Friendship Systems. Our activities are, we have several activities that we carry out, and we can operate in several fields of the consultancy. We can offer services related to geometrical optimizations. We have previous experiences with the CAESES team, and I will give you a few details later on. We are our very long-lasting field of expertise is the heat transfer, especially in engine component simulation of thermomechanical stresses and on thermal fields. We are very active on combustion side and on knock simulation and prediction. Furthermore, we developed during this year proprietary approaches for the sloshing simulation in tanks. We can simulate turbo machinery and in a single or multi-phase way, and we are now approaching in a very efficient way to the detailed chemistry, especially related to pollutant emissions and to knock behavior of the fuels. During these years, we developed some proprietary models, especially related to the heat transfer, to the knock in ALIS or RANS framework, and a statistical knock model that can be used in a RANS approach. As I told you a few minutes before, we can offer to the customers a joint consultancy with Friendship Systems team. as we have done in previous years. We can offer our high expertise on the fluid dynamics side in order to carry on the project from its creation up to the final report with the optimized geometry that can be delivered to our customer. I pass the baton to Mattia to introduce the topic of this webinar more in detail.
All right, thank you, Giuseppe. So now let's take a look at the example case that we worked on. So this, as I mentioned already, it's going to be an intake port. And as you probably know here, intake ports along with the valves that are located at the end of them are responsible for the mixture formation, especially in GDI and diesel engines. Also the charge motion, where you would like to create well-structured vortices so that you minimize the energy dissipation in the cylinder. And also they are responsible for the trapped mass of air that you will finally have in the cylinder for combustion. And this is important when you want to increase engine performance. So our topic today is an optimization of an intake port. And what we have here is a typical geometry of an SI engine. We have a pent roof combustion chamber, as you can see in the picture on the side, and 4 valves per cylinder. The design targets that were followed in this optimization are the maximization of the discharge coefficient or port permeability. Giuseppe will tell you more about all of these targets. The second one is the tumble ratio, and then these two were the optimization targets. We want to optimize these 2 values, and then in addition we also evaluated some other parameters like the turbulent kinetic energy in the region of the spark plug, as well as the swirl motion in the cylinder, or also known as omega tumble. Again, Giuseppe will explain these things in detail. So I will first of all take a look at the geometry side of the optimization. So for the geometry variation, there is different options that can be used within CAESES. You can use a parametric model, or you can use morphing techniques that are applied to an imported model. In this case, we used parametric modeling, and we used some special advanced surface modeling technologies that are available in CAESES. And to model, let's say, the main duct geometry in the port, we use this advanced parametric surface, which is based on a curve definition. So you start by defining a cross-section through the surface in question. And you see here at the bottom a cross-section geometry where one of the parameters is varied. And these parameters that define the shape of the cross-section will change their value in the direction of the surface, and that can be expressed by parameter distributions. So, for example, let's say you have the area, the cross-sectional area of your port cross-section, and that will change in the direction along the path of the port. And you can express this change in the parameter distribution, and this parameter distribution can then be controlled by parameters. And finally, if we combine the surface cross-section definition with the parameter distribution, we can generate the surface and then add all the additional components to make up the final geometry. So this is an, let's say, an efficient way of describing complex, also free-formed geometries in a parametric way, which allows you to have a lot of flexibility in the geometry variation while using a low number of parameters, as low as possible at least. So let's take a look at the parameters that we changed in this specific optimization. So let's start, the first ones are related to the cross section. And here we have a so-called ellipse factor, which basically defines if the cross section is circular or rather elliptical in shape. And this also has an impact on the area in this case. And in terms of parameters, we control this ellipse factor in 2 streamwise locations along the path of the port. These are the first 2 parameters. And then we have another 2 parameters that control the so-called eccentricity of the cross section, also in 2 different streamwise locations. And the eccentricity is basically the location of the center of area of the cross section. So you can see here in the animation that we go from a shape where the center of area is located above the middle to a shape where the center of area is located below the middle. Then we have another parameter that controls the angle at the inlet of the port. I think that's pretty clear to see in the animation, what kind of impact that has. Also the height of the inlet. And finally, we have a parameter that controls the straight length of the path at the inlet of the port. So you can see in the top view, so this controls in this in the Z projection of the geometry, it controls basically the curvature here at the outer side of the port. So these are all the parameters that we used in the optimization. In total, we have 7 parameters, and then we will see what kind of impact they have. And finally, one word about constraints. In this case, we didn't apply any constraints because it's, let's say, a special example case that we generated here. But of course, in an industrial application, you would want to consider certain constraints, and these typically concern manufacturing constraints. So for example, draft angles for casting, that you keep a certain minimum draft angle at the sides of the geometry, or a certain minimal radii because of the milling process, things like that. But also packaging constraints, which I mentioned before already, the distances to neighboring components. So in the picture, you can see, for example, an oil gallery on top of the port, and in red, it's highlighted the minimum distance between the port and this oil gallery that can be controlled. Or, of course, constraints can also concern other flow criteria that are not the ones that you're using as targets for the optimization. So you want to, let's say, minimize a certain value in the optimization, but you have a constraint on another flow property that it should not be worse than a certain value, for example. And finally, when we have the geometry model set up, we need to prepare the export. So in CAESES, you can export the final geometry in several generic formats like IGES, STEP, Parasolid, STL, and so on and so forth. And in this case, we're exporting to star-ccm plus, CCM, not CC plus, sorry, in a colored step format. And each geometry patch, as you can see in the picture on the side, gets a different color. And the color name that we have assigned, or the name of the color that we have assigned within CAESES, is used as a patch name in the export, so that you can very easily define different areas in your geometry in CAESES before you export it. And then when you import the geometry in star-ccm, you can identify the boundary patches by their name and address these different patches to assign, for example, different mesh settings or different boundary conditions. And that concludes the geometry part. So we have a parametric geometry model. We have defined the interface in terms of geometry export to the simulation code. And now Giuseppe again will tell us some more about the CFD setup and what we did in the optimization. And let me switch to Giuseppe. Yes.
Okay, thank you, Mattia, once again.
No problem.
Just a few words about the design targets that we defined during our optimization process. First of all, we defined a discharge coefficient that is the ratio between the actual mass flow rate that flows inside the ports and an ideal mass flow rate of air that flows through a reference section that in our simulation is defined as the sectional area of the cylinder on the equal pressure drop of the system. That means that during our simulation we computed the actual mass flow rate flowing through the ports, and we compared it with the ideal one flowing through a reference section on equal difference of pressure between inlet and outlet. Another design target that we defined is the Tembo ratio. It is given by the ratio between the flow angular momentum and the flow moment of inertia over a reference revving speed. In this case, we thought a revving speed of 6,000 RPM. We can see a simplified sketch of this computation, where it is possible to define a positive tumble ratio that is given by the red colored arrow, and the negative one that is given by the black colored arrow. And this is very, very important because during the intake stroke and then during the compression stroke, it is fundamental to preserve the motion of the flow in order to avoid energy dissipation. In this case, it is fundamental to reduce, of course, the negative portion of the tumble. Using this coefficient, this parameter, it is possible to include both the positive terms and the negative terms as well. This computation that is given by the summation of all terms cell by cell is performed over a volume equal to the stroke times the bore of the cylinder. It is important to understand that discharge coefficient and the tumble ratio are challenging a competition. I mean, the higher is the discharge coefficient, the lower is the tumble ratio, because during design, a port design optimization, it is very difficult to meet a good trade-off in order to have well-organized, well-structured flow motion inside the cylinder with a high tumble ratio and a very high discharge coefficient, because of course the curtain portion of the valve is used in a very different way if we want to give a motion to our flow, or if we want to use the entire section to fill in the cylinder. As Mattia stated before, we took into account two evaluation parameters as well. They are not targets for the optimization, but of course we have to take care about them because they are important during the port design. They are the turbulent kinetic energy in the spark region, because of course it is important to have a high level of turbulence very close when we are very close to the spark plug. And we have to consider that there are some secondary motions, secondary flow motions inside the cylinders, such as swirl motion, or in SN engines they are defined as omega tumble motions, that are characterized by a flow motion whose axis is parallel to cylinder axis, and they are not so desirable because they dissipate energy and they can affect the flame front propagation during the combustion. Then we want that these omega tumble motions are as less as possible. And they are defined, the omega tumble is defined in a similar way as we did for the tumble ratio. Moving to the CFD setup, we reproduced in our simulation what is usually done at a steady state flow test rig when intake and exhaust lines are tested. I mean, we reproduced the intake ports, and we used the intake ports and the dome of the combustion chamber, and we added a plenum in order to take into account the environment. Piston, of course, is not included in the computational domain because this is a steady state flow motion of the intake port. Then we considered just half of the computational domain in order to save time. This is crucial during optimization processes. And we extruded the outlet boundary in order to allow the flow to develop and to do not be affected by the boundary conditions that could be too close to the cylinder dome. In order to take into account flow separations and all fluid dynamic effects that could affect, of course, both discharge coefficient and tumble ratio, we used a low Reynolds approach for our mesh. We used 12 layers next to the walls, and with an overall number of cells that is approximately equal to 600,000 on half of the domain. And this led us to need about half an hour for each design from the mesh, from the geometry generation by CAESES to the output results. The boundary conditions were defined with a total pressure at the inlet and a static pressure at the outlet, of course, and we imposed a symmetry plane at our geometry. The simulation is steady state, and we used the K omega SST turbulence model in a RANS fashion with a low Reynolds wall treatment approach, as I explained before. The operating flow is air, modeled as an ideal gas. And of course, once the pressure drop is imposed, the mass flow rate of air through our system depends on the effectiveness of our geometry. I mean, it depends on the port permeability. The process we followed started with a preliminary step where a DOE analysis was carried out using a Sobol algorithm, where we had at the end 40 investigated designs in order to capture the driving factors during optimization and to find some relevant correlation coefficients. Then we moved, thanks to this DOE, we moved to the optimization. It was performed in two subsequent steps, each one starting from the previous one. So the first optimization performed with the Dakota algorithm started from the response surface calculated by the DOE during the step 1, and step 3 used the results obtained by step 2. Here it is, the animation of all the geometries we investigated during our simulations, during our optimization process, and they were all successful during the generation by CAESES. In the right part of the slide, we can see the flow field that deeply changes while the geometry changes, of course. And this is the reason why we had very different results from one geometry to the other. Just to give an idea about the output that we can have from an optimization process, it is fundamental to understand that once we identify our targets, that in our case are the maximization of tumble ratio and discharge coefficient, it is very important to understand which are the geometrical parameters that can affect deeply the variation of our design targets. In this slide, I depicted the variation of both tumble ratio and discharge coefficient with some geometrical parameters that are, in this case, for example, eccentricity int 1 and eccentricity int 2 that Mattia explained before. We can see in the lower part of the slide the external values, how the geometry appears when the parameters are at their minimum and maximum. The dashed lines that are colored as the points that are depicted into the graphs are the correlation coefficient. The higher it is the absolute value of the slope, the higher is the correlation between the design parameter and the geometrical value that we are investigating. In this case, for example, if we consider the red colored dots that represent the tumble ratio, we can see that the dashed line is pretty horizontal. This means that there is practically no correlation between the tumble ratio and the variation of the eccentricity. And the same is, for example, in this case, for the discharge coefficient. It is very different instead if we consider the eccentricity int 2 parameter. We can see that there is a high correlation between the discharge coefficient and the variation of this value, and an anti-correlation, because the slope is negative in this case, between the tumble ratio and the eccentricity int 2 parameter. Same considerations can be drawn for the evaluated parameters as well. We can see that they can be affected by geometrical parameters, as for example the swirl ratio and the eccentricity int 2, or completely not, as it happens for the turbulent kinetic energy at the spark and eccentricity int 1 design parameter. And practically the same can be seen if we compare the behavior of the evaluated parameters along with the variation of eccentricity int 2. Another important consideration that has to be drawn is that not all the geometrical parameters affect both the design targets. For example, if we have a look to the inlet angle, we can see that it deeply affects the tumble ratio, but does not affect the discharge coefficient. Conversely, if we have a look to ellipse factor, it is deeply anti-correlated with the discharge coefficient, and it is practically not correlated to the tumble ratio. This means that, for example, the higher is the ellipse factor into parameter, the lower is the discharge coefficient. Then we hope that our designs can be as close as possible to a value equal to 1 of this factor. Thanks to this preliminary DOE investigation, we are able to analyze a distribution of solutions, and a very preliminary Pareto front can be traced. The Pareto front is the region of the diagram where all the best results lie. Of course, this is an approximation of the Pareto front just to give an idea about its shape in our design. Thanks to these preliminary solutions, we then moved to an optimization using the Dakota algorithm. Thanks to the Dakota algorithm, if we plot on the same graph the results deriving from the DOE analysis, that are the light blue ones, and the results deriving from the optimization process, that are the red dots, we can see that there are a lot of solutions that are the best trade-off for discharge coefficient or tumble ratio. This graph, in fact, is the reports the variation of discharge coefficient along with the tumble ratio. And we can see, for example, that there are some points that are very close to the results obtained with the DOE analysis, but they are able to improve a little bit then. Furthermore, there are some points that are in a very different location, and this is, of course, a result that we want to investigate when we run an optimization investigation. If we have a look using this polar diagram to the range of the design parameters, just using a threshold including the best solutions, I mean the solutions that can identify the Pareto front of the optimization process, we can notice, for example, that all best solutions are characterized by a very narrow range of the inlet angle parameter and of the linear length zeta plane parameter, as it is highlighted into the slide. This means that we expect that all the best solutions will be characterized by a very, very short path for the linear portion of the inlet port, of the intake port, and by as high as possible angle for the inlet duct. As a last step, starting from the results given by the first optimization, we run a further optimization that was able to refine, first of all, the Pareto front. As we can see, there are a lot of points that are very able to fill the design space. And furthermore, we can see that there are some designs, for example, the one highlighted into the slide, that is able to increase the discharge coefficient with a reasonable reduction of tumble ratio. For example, if we have a look to this, to all these designs, we can see that there is just one that is able to have a gain of discharge coefficient, improving or not reducing too much the tumble ratio. For example, it depends, of course, on the application that the engine is designed for. But this, for example, could be a very good trade-off in terms of design choice. If we consider, for example, the flow distribution through the curtain, the valve curtain, we can see that there are a lot of flow rate flowing, for example, through the rear portion of the valve. Of course, this is the explanation, for example, for the reduction of the tumble ratio, because if we are feeding the valve curtain in the same way all over the circumferential portion of the valve, the higher will be, of course, the reverse tumble that will reduce the tumble ratio that we are computing. Just to conclude, if we have a comparison between the baseline that we designed without any kind of indication, but just thinking about a good geometrical solution, we can see that there is there is a room for the optimization that leads to an increase of the discharge coefficient in the optimized solution, that is the yellow colored one, with respect to the baseline solution, that is the green colored one. Of course, this increase of discharge coefficient will lead to a small reduction of tumble ratio. Then the meaning, of course, of this diagram is that we are now able to choose the best solution to solve our need in terms of discharge coefficient or tumble ratio. I pass the baton once again to Mattia, and I want to thank you everybody for your attention and for your attending this webinar.
Yeah, thank you, Giuseppe. So now it's my turn to conclude the webinar. First of all, telling you what to do next. So would you like to get to know CAESES, or do you have any specific optimization problem that you would like to work on? One thing you can do is check out a special Powertrain promotion that we have at the moment. If you go on the website bit.ly/xmaspowertrain or bit.ly/xmaspowertrain, as you can see here, you can see this special promotion, and you can also use the promotional code INTAKEPORT that you're reading here to get 20% off on that offer. Of course, you can also get in touch with us. Here are our email addresses or our websites. So if you're interested, don't hesitate to get in touch with us. We have about 5 minutes left. Before I fully conclude the webinar, there's 2 questions that we can maybe try to address very quickly. Giuseppe, maybe the first one can be answered easily by you. The question is, why do we have a spherical boundary condition at the inlet? What is the significance?
Okay, the reason is that this kind of boundary shape, I mean, allows us to mimic in the best way the environment. Because of course now we added a fillet to the port in order to link it to our environment. That is usually what is done during the simulation. But once you can use a spherical boundary for the inlet, you are avoiding that your flow could be oriented in some way. If you use, for example, a box, it has to be large enough to forget the presence of walls, for example, or you should, for example, use a squared box large enough but with all pressure inlets. I mean, this is the most effective way to reduce the number of cells and to avoid that that boundary condition could affect the behavior of the port.
Okay, yeah, I think that's pretty clear. And there is a second question, which I can try to answer. Maybe you have something to add, Giuseppe. The question is, can I simulate fuel injection with different fuels? And just first of all, preliminarily, as I mentioned in the presentation, if you're running an optimization, you can, of course, apart from the geometry parameters, you can also include some other parameters that are related to the, let's say, physical behavior of the system. For example, you can control injection timing, the profile of the injection, spray angle, and so on. And I assume, without having too much knowledge about this, that you have also some parameters in your in the input to your simulation code where you can control the chemistry of the fuel, I guess. And if that is the case, then of course you can also use these parameters in the optimization or in the parameter study that you're doing. Maybe there is something to add from your side, Giuseppe.
Yes, it's totally correct. I mean, if you use different fuels, of course, your spray will behave in a different way. Then the only thing to do is to build an optimization where there are, of course, there are more objectives, or you will need to set up a unique target function where all the different targets will be included, of course. But yes, it is just a matter of increase the simulation and to be very confident on your spray simulation. Then it can be done, of course.
Okay, great. That was it. That was it in terms of questions. I think we're pretty much spot on in terms of time. So it's almost 4 o'clock now. So thanks again for joining this webinar. As I said before, don't hesitate to get in touch with us if you would like to discuss some matters in more detail. And yeah, I hope to see you in one of our upcoming webinars or to hear from you. And until then, have a good time and thanks for coming. Bye-bye.
Thank you very much. Bye.